let's finish them. I have the recording going, and okay, the lab is short, so, and if anybody has to leave, they can leave. I can just post the problems. Okay, this self-inductance and capacitance of an oscillating circuit are that, respectively. What is the frequency of oscillation if the maximum potential difference between the plates of the capacitance is 50 volts? What is the maximum current in the circuit? Okay, so, oops. So here's a capacitor, here's an inductor, and this is an oscillating circuit. And okay. The frequency of oscillation is given by 1 over square root of LC. Yeah. So this is the angular frequency, and square root of L is 20 millihenries. And capacitance is 10 minus 6 farads. Okay. So let's take care of powers of 10. This is 10 minus 2, and 10 minus 8. Square root of that is 10 minus 4, and that comes to the top. That becomes 10 to the 4. So 10 to the 4 plus square root divided, and that's 1 over seconds. Okay. So this is equal to Alright, so that is 7.01 into 10 to the power of 3 radians per second. Okay, so, and if you divide by omega by 2 pi, gives you F, and 2 pi is roughly 6.4, so roughly 1,000 hertz. Okay. So, and what is it? Part B, if the maximum potential difference between the plates of the capacitor is 50 volts, what is the maximum current in the circuit? Okay, so in this, you can look at your notes. Here the charge is varying sinusoidally, so is the current varying sinusoidally. Okay, and you can look up the expressions in your notes. So the charge on the capacitor varies like so. Q max cosine omega t or sine omega t, it doesn't matter. Okay, so, and so they give you the maximum voltage. So for the capacitor, on the capacitor, the voltage across the capacitor is equal to the charge across the capacitor divided by C. Okay. And since Vmax, so Vmax is equal to Qmax divided by C. Qmax is Q naught divided by C. Okay. So we are going to evaluate Q naught. Q naught is Vmax times C, and they give you that to be 50 volts. So you can see that the maximum potential difference between the plates is 50 volts. On the capacitor is 50 volts. So that's 50 volts, and it's 1 microfarad. Okay, so 50 microcoulombs is the maximum, is Q naught. Okay. So now we have Qt as an expression, as a function of time. 50 microcoulombs divided by cosine omega t, and we already have omega from the previous part, from part A. Okay, so now what is the maximum current in the circuit? So the maximum current in the circuit is dq by dt. The current in the circuit is dq by dt. Okay, so let's add a page. Okay, the current in the circuit is dqt by dt. The negative sign just is telling you about the phase, so that doesn't matter. Okay, so IT equal to, we'll call this I naught sine omega t, and I naught is the maximum current. Microcoulomb times, we figured out omega 7.07 into 10 to the power 3, 1 over second. And so this works out to 0.35 amps. Okay, so that is the amplitude of the current. Oops, that's not what I was trying to do. Okay, so this, what we have found is the amplitude of the current is 0.35 amps sine omega t. Okay, so that's the sinusoidal current in the oscillating circuit. All right. So I'm not going to ask any questions because I just want to go ahead and finish the next problem. In an oscillating RLC circuit, okay, so this is in the previous problem, okay, so this circuit, if you set up a current in this circuit, it will oscillate forever. Why does it oscillate forever? There is no friction. There is no dissipative elements. Soon as you put a resistor kills good energy. It turns good energy into heat. Here in this circuit, energy is being stored only in electric fields and magnetic fields, and it'll oscillate forever. Okay. Now, if you so in this circuit, you have to deal with reality, and with, unfortunately, with, or well, in reality, you have a resistor present. Okay, so and what you will find is, let's say Qt is the charge, and this will I looked up the expression, yeah, 2 over L cosine omega t omega dt. Okay, so, and the frequency changes slightly. Okay, where so that we're not concerned with. The subscript D telling you it's a damped circuit, where omega d is 1 over LC minus R over. You guys will have to look up this. Can you check this expression? So when R equal to 0, it goes back to the normal frequency. Okay. Anyway, so here's what's relevant to us. So you see the amplitude of oscillation is dying exponentially. Okay, and that's what matters to us. And how much time lapses before the amplitude of the oscillation drops to half its initial value? So its initial value is Q naught, and at what time will this become a 1/2 is the question. Okay, so what we want is e to the power of minus RT by 2L to be half, assuming this expression is correct. Okay, and you guys can check this, and if it's not, then I'll fix it later. No, I won't fix it later because this is being recorded. Okay, so anyway, you take the logarithm of both sides, minus RT 2L equal to T equal to negative 2L divided by R. So at this time, the oscillation amplitude has died to half its value. Okay. So let's plug in the values. 2, what is L? 10 millihenries. R is 2 ohms. Okay. .69, so 6.9 into 10 minus 3 seconds. 6.9 milliseconds. So after 7 milliseconds, the oscillation amplitude has died to half its value. Okay. And on that note, we